We've been asked to find the flux of this particular vector function through a cylindrical closed surface. Closed here means that we're including the top and the bottom as part of this surface. And that changes what we're doing. So we're going to do this traditionally as a flux integral first, as a surface integral like we would have done in section 16.6. So as a surface integral, we have our surface integral of f dot ds, and that's going to be the surface integral of the cylindrical side plus the surface integral of the bottom of the can plus the surface integral the top. So it's the flux out through the sides plus the flux out through the bottom plus the flux out through the top. And so actually we have three surface integrals to do. This is good review of how these work since it's been a weekend for us, maybe since we've done them. We have to parameterize the cylinder. To do the cylinder, the parameterization is 2 cosine theta, 2 sine theta, comma z. The parameters are theta and z. The normal vector, if we go through the process of finding the normal vector, what is that process? That process of finding the normal vector is going to be find the tangent in the theta direction and the tangent in the z direction. The tangent in the theta direction will be minus 2 sine theta, 2 cosine theta, comma 0, and in the z direction it will be 0, 0, 1, and the cross product of those two is how we get our normal vector, and that will turn out to be 2 cosine theta, 2 sine theta, comma 0. That 0 on the z component, that makes sense if you think about the normal vector out the side. It is flat. It's not pointing up or down, so the z component should be 0 for the normal vector, and it in fact is. So if we set this up now, our z integral is 0 to 5, our theta integral is 0 to 2 pi. We have our function, and the function that we're integrating is y comma yz comma z squared. So y on our surface is right here, 2 sine theta. Yz is 2z sine theta, and then it was z squared, so that's z squared, dotted with this normal vector, d theta dz. So we'll have some sine cosine products here. We'll have sine squared. For sine cosine, we use a u substitution. For sine squared theta, as part of the integral, we use the identity that sine squared theta is 1/2 minus 1/2 cosine 2 theta. That's how we do those integrals when it comes to it. What we're going to get out of this, using those techniques, is 50 pi. So that's the flux out the side. We also have to find the flux out the bottom of the surface, the bottom of this can or cylinder surface. On the bottom, f, remember f is y comma yz comma z squared. On the bottom, z equals 0. So it's y comma 0 comma 0 for the vector field. The normal out the bottom is 0 comma 0 comma minus 1. So the dot product of f dot n ds, the dot product is going to end up giving us 0. So there's no flux out the bottom, and that's just a function of what the vector field is. The thing that we're integrating happens to be 0 down there. So that's good news. And out the top, at the top, z is equal to 5. So for the top, we have our vector field is y comma 5y comma 25. Our normal vector is 0, 0, 1. Right? When I said bottom, the normal was 0, 0, minus 1, top 0, 0, 1. That's just a function of what we're looking at here. The cylinder, the normal out the top, has no x, y component, z component positive 1, and out the bottom it's z component negative 1. So let's see, we end up with an integral of y comma 5y comma 25 dotted with 0, 0, 1. And that's going to be the double integral over the, it's going to be over this region down here in the xy plane. So over x squared plus y squared less than or equal to 4 of 25. So if we think of that as, pull the 25 out, we're integrating 1. We know then this is the area, 25 times the area of D. The area of that circle down on the xy plane is pi r squared, so 4 pi. So this is 100 pi. Overall, the total flux out the side was 50, flux out the top is 100, out the bottom was 0, so the total flux is 150 pi. And that's the answer. That's the total flux out of this surface. If we had not recognized this fact of this being an integral equal to the area of the circle, then we would have just done the integral in polar coordinates and we would have gotten the same thing, and it wouldn't have been a whole lot of work to get there. But that's flux traditionally as a surface integral. In the next video, we're going to look at the same problem using the divergence theorem to do this as a triple integral instead.